Okay, so if you haven't taken a look at the homework, please start to look at the homework now. Um, it's there either it looks too easy at first or it looks too hard at first. And I think the truth is it's somewhere in between. It's not easy, it's not trivial. I definitely think you'll want to make use of reference classes, and you probably won't get it right the first time through, so you're going to have to make adjustments as you test out your code. So start working on it now, and that way you can ask questions, and I'm happy to try to answer questions about the homework. I think, well, I don't know if this is an interesting case. I like board games. You know, obviously the class is going to be modeled by or molded by the things I find interesting. So things like sports and baseball and board games sometimes make their way into the course. And you know, Monopoly is not the greatest board game of all time, but in terms of you know, being able to simulate token movement around the board, I think it's something that's doable, but at the same time complex enough that it's not just every square has equal probability. Okay, so try that out and get started. And you know, if you have questions, let me know. Are there any other issues, comments about the course? Not yet. Okay, so today I'm going to so now again we're moving into this realm of computational statistics, and so today is going to be a little bit more board work based, theoretical, and so we're going to talk about simulating random numbers. Okay, and within R, we're going to just start off kind of with the premise that we can generate random variables or random numbers from the uniform distribution from 0 to 1. Okay, so so we're going to start with this kind of, I guess, assumption or given. And this is not trivial, but at this point, our computers are able to generate random numbers from the uniform distribution with such good properties that we can almost treat it as if it's a solved problem and not something that we have to worry about. You can look up on Google, you can search for you know, pseudo random numbers, random number generation, and there's going to be these long articles on how these things work, the Mersenne twister and all of these things based on using prime numbers and getting sequences of random numbers here. But if effectively, you know, we have some zero, one, and you know, our density, we'll have a height of 1, okay? Because this is our probability density function. So our PDF will be equal to f of x equal to 1 for 0 less than or equal to x less than or equal to 1, 0 otherwise. Okay, and this allows us to have a cumulative density function or our CDF, which we often write as big F of x, okay? And this is equal to x, so we're essentially or is it, what is it, 2x? 2x, right? Okay, for 0 less than or equal to x less than or equal to 1, okay, and 0 otherwise. Wait, no, it's just x, huh? Sorry, confusing myself here.
But it's not 0 otherwise, it's like if x is less than 0, then it would be 0. If x is greater than 1, then it would be 1.
Oh, yes. Sorry. Very good. For, and then 1 for, and so our function looks like this. If this lines up correctly, it's not quite right. Okay, and so we're just assuming our, and you can do this with R using the function R unif 1, and this will just give you one random number. This generates random number from the uniform distribution. Okay, or you can you can ask for 1,000. This will give you 1,000 random numbers. Just see here. Okay, and so now that we, if we start off saying we can generate from the uniform distribution 0, 1, we can then expand this to start generating numbers from other distributions as well. Okay. Now there's kind of a balance because R can already do a lot of the type generation of random numbers that you might want to do, but I think it's still worthwhile to talk about here. So let me talk about this. Okay, so let's say you have another distribution that you want to generate random numbers from. Okay. And so in this case, we're going to take the the cumulative density function. Okay, so let's say we have the desired distribution is g of x, okay, and then the desired distributions CDF is capital G of x, okay, and then and the idea here is we graph the CDF, and maybe it looks something like this, okay. Right, so starting at 0 and it goes up to 1. Okay, so this is the CDF G of x. And the idea is so this is called the inverse transform method. Okay, sorry. Okay, so we will generate a value u from uniform 0, 1. Okay, so whatever this value is, we get this right here. Okay, and then we go over to the CDF right here, and then we find its corresponding location right here, and then now x has come from the distribution g of x that we want. And this works out well if g of x is easy to solve for, and if it's easy to go from g of x, big G of x, the CDF, to the PDF. Okay, so so you know, we find, so in this case we find where g of x equals u, okay, and then the corresponding x will come from g. So if essentially x is equal to g inverse of u. Okay, and so the inverse transform method works well in situations where g of x can be found easily, or is known, and g inverse of x is easily computed. Okay, so let's we'll try an example here. Yeah, I'll wait till you guys finish writing, or So here's an example. Of the so we're going to start off with some density. Our desired density, we'll say our desired density will be equal to 3x squared for x between 0 and 1. Okay. So if we were to graph this, we have this starting at 0, we get this parabola. I guess that's it. So this will be g of x, okay? And so big G of x is the CDF. It's the integral from 0 to I guess 0 to x. And then we have to write some other letter like 3t squared and dt. Okay, and so this just becomes x cubed, I believe. Okay. Also for 0 to x less than 1. Okay, and so in this case, this thing's going to look exactly the same. Right. I mean, it's a little bit more flat in the beginning. Exaggerated. Okay. And it looks like that now. Okay, and then so what we're going to do in R is, let's say we want to do generate a random number. We'll have u, and then we can do R unif. We'll say 1,000. Okay, so this will be 1,000 random numbers between 0 and 1. Okay, and so here we go from 0 to 1 there, and we're just drawing 1,000, okay, from across there. So we have g of x, so g inverse of x is, what time, what function, right? G inverse of x, g inverse of big G, will give us 1. So our g inverse function is going to be x to the 1/3 power. Okay, so we're gonna plug in our u into our g. So we're gonna do u raised to the negative 1/3. Okay, and then so these values, so I guess we'll store this as x, okay, and then so x is now distributed with density 3x squared with g of x. Okay, so we can test this out. Let me create a new script here. So we say U is R unif 1,000. And then we're going to say X is just U raised to the, did I say negative 1/3? It should just be 1/3. I'm sorry. I know I have that here. Okay. All right, and then if we just do, we're going to just create a histogram of X, and I'm going to graph the kind of fitting a probability curve. Oh, well, not. Oh, I'm sorry, not the. So this gives us our density here, okay, and then we can add a curve. So let me just we're going to do lines of a sequence. Let's see, sequence from 0 to 1, and we'll do increment by 0.01. So this is just going to create it, and we're going to graph y, lines y, and then 3 times y squared. So this will add a density curve here. Okay, and so this is after 1,000 random draws. We can see the randomly generated numbers that we have kind of fit our density. If I did 10,000, it would probably give me a better fit. Okay, and so this looks to be that looks pretty reasonable. Okay, and you know, if we want to just kind of make sure that if we expand our x limits, we can go from like negative 0.5 to 1.5. And yeah, so our data only exists between 0 and 1, which we would expect just considering what we've generated, but indeed this would fit the density here. Okay. All right, so I'll snap this. Okay, and this would work as well for discrete distributions as well. Okay, you just the formulation is, instead of an integral, you now have kind of a summation, but we can do it for the discrete case as well. But I think I'm going to move on to the accept reject method for generating random variables here. Okay. All right. I guess I can post examples of the discrete case as well. All right. Is this okay? Any questions? So this is. I know it's a little bit of it feels a little bit different, but this is entering our computational statistics and all of this. Yes.
I'm a bit confused on the point of this method. Are we using the distribution of gx to find a distribution of x?
So here what we're doing is using the fact that we can generate a uniform random variable. Okay, so the question was, what's the point of this? So we're going to say we can generate uniform 0, 1, no problem. Okay, what if we have another distribution that we want to generate random variables for? Okay, so someone says, the random numbers are generated based on this distribution. So, I can't think of situations off the top of my head, but let's say there is some way where the numbers are generated another way. R may or may not have a function that allows you to generate random numbers from this whatever particular density that you do have. If you can get the cumulative density function and the inverse of the cumulative density function easily, this is a good method to use. There's no, quote, wasted numbers here. You generate a random number, u, and that gives you the corresponding x to use. And so in that case, it's very useful. The hard part is unless you have a nice density function, it's sometimes really difficult to get the CDF and the inverse CDF. But I don't know if that answers your question about what the point is.
So how are we going to apply x to the new density function?
How do we
Apply x to the new density function?
So x comes, so if you generate the random uniform and then you apply the inverse CDF function to the uniform numbers, the result you get is x, and x has been generated from the desired density function. So if you wanted to ask questions like, what is the mean of this density function? Okay, so it looks like the mean is around 0.75. If you want to know what's the standard deviation of this, or what's the variance of this, we can ask all of these questions, no problem. It's just so x now behaves as if they were generated from this other density function, not the uniform, right? Because if I just did a histogram of u, okay, these are 10,000 numbers. It looks like this. Okay, so fairly uniform. I mean, it doesn't look like they're super uniform, but that's just because they're random numbers, right? If I did 100,000, it would look more like it. Of course, some variation, and then I can apply the inverse, and in this case, it fits very, very well. So these numbers are just, these come from the desired density function that you want. That's all. So part of this is if you need random numbers from another density function, this is the way to do it. Okay. Another way. So sometimes we can't get the CDF. Like the g of x is, your density function. In order to get your CDF, you have to be able to do an integral. And sometimes it's not possible, okay? Or it's really hard to. So in that case, another method is called the acceptance rejection method. Okay, so let's say our desired distribution is g of x, okay? And then we have a known other distribution, f of x, okay? And so what we do is we do g of x divided by f of x, okay? And we find kind of the ratio between these two values such that this quantity is always less than some number c. Okay, so even, you know, if g is bigger or smaller or whatever, we can just find that this thing is always less than some number c, okay? And then so what we do is we take a random variable, generate a random number from f of x, okay? And then we generate a random number from the uniform, from uniform 0, 1. And then what we do is we, if we know this value c, okay, we calculate basically g of x divided by c times f of x, okay? So that, and the reason why is because if we multiply this thing by c, then this quantity is always going to be less than 1, right? So, okay, so this, by multiplying the denominator by c, we know this quantity is always less than 1, okay? And so what we do is we compare the random number we generated from the uniform, so we compare u with this quantity here. Okay, and if, oh shoot, okay, sorry, generate a random number from f of x, I'm sorry, I need to say this is y, I apologize. And then we compute this quantity here. So we plug in y into g of x and f of, into the function g and into the function y, sorry. So we plug this in here, okay, and if u, the uniform number, is less than this quantity, then we accept y, okay? And if not, we throw away y. Okay? And so all of the y's that we end up keeping will come from our desired distribution. Okay, so I'll let you guys write all of that down, and I'll try to illustrate how this works. Okay, so the idea is we've got two distributions going on. You've got the g of x that you want, and then you have this other f of x that you know you can generate numbers from, okay? And so we can take this, the f of x, as the uniform, but it could be anything else as well, okay? So we generate numbers from f of x, and then we calculate this ratio between g and f, and then we compare that versus the uniform, okay? So do you guys have this written down? All right, so let's say we have our same g of x that we want, and that's, what is it, 3x squared? Okay, and then let's say our f of x is going to be the uniform, which is basically just 1, right? Same type of thing. We've got this going on, 0 to 1, and so at 1 this is up at 3. Okay, and our uniform goes like this. So maybe I'll pick a different color here. So this is g of x, and over here we've got f of x. So we're going to use c, okay? If we look at g of x divided by f of x, okay, this is the max value it takes is 3. Okay. All right, so our c is going to be equal to 3. So basically we're just going to multiply f of x by 3. Okay. And so we pretty much have the same thing now. And then, so this is now, f of x now is up here. This is now 3 times f of x. Okay. And so what we're going to do is we're going to generate a random number from f of x, okay? And so when we generate random numbers from f of x, all these numbers are equally likely. All the numbers between 0 and 1 are equally likely, okay? But when we look at the density of g of x, we see that these ones should appear much less often than these ones over here, right? So this is what happens. This is how we take care of that, okay? We're generating numbers at over here. This is kind of uniform. And then over here, basically from 0 to up here, this is 0 to 1 if we do the ratio. These come from a uniform distribution. So, you know, it's a coincidence that both are uniform in this illustration, but it doesn't have to be, okay? And so we look at, we're generating from 0 to 1 over here, kind of, okay? Or we are. And basically, let's say I generate a number right here, okay? And so if the uniform number, so I'm going to draw a vertical line, if the number u that I generate happens to be less than this location, okay? So this is this is our point, g of x divided by 3 times f of x, right? This location, this height, represents the different g of x divided by 3 times f of x. And it works because I can draw it here because f of x is uniform. If f of x is not uniform, then I can't draw it on the same axis here. But yes.
What would be the point of having f of x be something other than uniform?
I'll explain, okay? So we generate this. If the u that happens to be generated is less than this thing, we accept it, okay? So if u is lower, we accept. Otherwise, if it's over here, this is thrown away. Okay, and so we can see for values here, only a certain fraction will be accepted. And over here, quite a few will be thrown away. Whereas over here, almost all of them are going to be accepted. Okay, does that can you guys see that? Okay, and so here we're calculating the ratio between the known distribution or the known density and the desired density, and we generate a uniform number. And if that uniform number is smaller than this ratio, we accept it. Otherwise, we throw it away. And so we can see, as we're generating numbers, pretty much all of these, everything out here, this whole region gets kind of thrown away. So any point that's generated, you do the calculation, these all get thrown away, and only the ones down here get kept. And that's how we make it so that the x's we keep follow the desired density. Okay. So the question is, why would we want to use anything other than the uniform? Well, for something like this, we can see we're throwing quite a few of our random generations away. Okay, so let's say we have a hard time generating directly from this. We might be able, somehow, let's say we've got this thing going on. We might be able to have a density that looks like this. Okay, we might be able to generate from a known density that looks like that. Okay, and this way only this part gets thrown away, right? And if we were to, our picture no longer works here, we would have to take the graph of the picture of the ratio between these two will end up looking more like this, something like that, okay? Probably a little bit more exaggerated. Something like that, okay? And so in this case, only this part gets thrown away. And these are accepted because, these ones under the green distribution, these numbers are not going to be generated as often to begin with, okay? And so even if they're not generated that often, if they get thrown away, if we keep them more often, it still ends up following the correct distribution because the f of x doesn't generate these values as often in the first place. Does this make sense? Question? No? Okay, so this is the acceptance rejection method. So, oh shoot, okay. Let's see if we can do this in R. Okay, so over here, we're just going to say our, we'll call g of y as a function of y. Okay, and actually it's just g. G is a function of y that will return, what is it, y squared? No, 3y squared, I'm sorry. Okay, so we're going to generate our method is we're going to generate u, and then we are also going to generate y coming from our uniform. And we're going to calculate whether g of y is that less than u? Okay, so I'm generating 1,000 uniform numbers. Hang on a second. I'm doing this wrong, aren't I? So this is kind of our decide to accept. This is the y's coming from known distribution. We're going to take our 3y squared and we divide, we take the ratio between g and f. Oh, okay, so f is actually just 3. So basically I'm going to do g divided by f, g of y over f. And if the uniform, if our u is less than g of y divided by f, okay, this is whether we keep or not. Can you guys follow this code here? So we're generating numbers from u. These are just random uniform. We're also generating random y's here. We calculate g of y. We divide by f, which is just 3. And if that ratio, if u is less than that ratio, we keep it, okay? And then we just apply that to our y. So we subset all of these random numbers y on whether we should keep them or not. Okay? So I'm going to do this. Run, run, run. We do that. Okay? And so I guess I'll say this. So let's just look at our x, length of x. Okay, so even though we generated 100,000, we kept only about 33,000 of these, okay, because we're throwing away quite a bit. So we can create a histogram of x just to kind of see if this okay, but it looks good, right? Our histogram looks good. So these are the x's that we use the acceptance rejection method for. Maybe I'll call this z. Oh, yes. Oh, question? No. Okay, and we apply our density and it fits. Okay, so this is a method also to generate using the accept reject. It's just a lot of times the numbers that you generate will get thrown away. All right, so I'll include this in our notes as well. Okay, so we'll end there. Start your homework, and that way if you have any questions, you can ask them now.